Actually, I did have to go out at about 5. It's pretty nasty out there. But the rest of my sessions tonight are all in. So area under the curve.
Yes.
Do you have some?
Since I have this, since you've heard about my math IA, right?
Your what?
My math IA?
Your math IA. What is that?
Yes, the one that I talked to you about of having the light at a different angle. Well, my teacher said that my problem was too simple, so I had to complicate it. And I'm finding the area of one particular shadow.
Okay. Now I remember.
However,
Yeah, you're talking about that. Okay.
yes, however, I had to change it from having it at a different angle to having two lights, one at 30 centimeters above a surface, and the other one 13 centimeters above a surface,
Okay.
and then move a cube between the two lights to see at what point do I get the most optimal light coverage.
Okay. Is that the problem you want to work on tonight?
Yes. Since I had forgotten how to find the area under the curve.
Well, that's not going to be area under the curve.
I mean, as in like minimizing the shadow.
Okay, that's going to be an optimization problem.
Right, but
We can find a function, and then we'll want to take the first derivative, set it equal to 0, and find those values.
no, but you see here, so I figured out most of the areas, but at this one part, I'm having technical difficulty.
Okay.
And here, I'll send it now. I didn't think to send this before.
Go ahead and send it. I'll take a look at it because I'm still having a little trouble picturing. So this would be a side view of the cube. And you have a light that is how much? 7?
centimeters.
So this distance is 13 from the top of the light to the center of the top face of the cube.
Yes. I also had a piece of paper underneath it, so I also measured it from the end of the piece of paper.
Okay. And so, in other words, it's these angles.
No, I'm not dealing with angles.
All right. Well, I'm going to have to wait till I get a copy of it because I'm not being able to picture this. In other words...
Oh, I sent the picture just now of one of the shadows.
All right. Maybe if I look at that picture, I will have a better feel for this problem. Trying to figure out what I'm looking at here. Where's the cube?
Here, I'll send a picture of a different shadow. That way you can kind of see.
Is this area over here the shadow?
The entire outline is the shadow.
The entire outline from here to there to there.
Okay, so
Goes off the page. How do you get this kind of a shadow from a cube?
I had two lights, and that curve right there is from the other light.
Each of these points here are a light bulb?
No, no. I had those points so that way I could figure out the curve. Since I didn't have the original curve, I just had that curve. So I figured out what the curve was.
How'd you figure out that quadratic?
I plugged in the points into my calculator and then...
Did a quadratic regression?
Right.
And got that curve. Okay. So what is the problem? Is it to find the area under this curve between this x-axis from this point to this point?
Right. Since I did it by parts, I turned it into a...
You did an integration
block.
by parts?
No, I was figuring out the area by parts. So what I was doing, the area of the triangle is 36, and I had the block,
Okay.
and then I subtracted the 71.25 since I was a triangle.
Okay.
And now I'm trying to subtract this area.
So everything else is a straight line thing, all the rest of this stuff.
Right.
So the only problem you have is finding out.
The rest is all straight line.
So the only problem you have is finding this area.
Right.
The area under the curve is the integral of the function from, if it's this point to this point, that's what it is. So it's the integral of that function. And that's fairly easy to integrate. We can use the power rule. So the only thing that we need are the limits of integration. Well, it looks like this goes 15, 20, is that 31 there?
Yes, actually I was doing it from 20.5, since right there that would be a triangle.
Right, so you can figure out that little area there using geometry.
Right.
What we need calculus for is to find the area under curves. So that's what it would be, is let's write it out. Straightforward. I mean, I don't need to understand the problem to be able to help you here, I don't think, because I still don't understand the problem. But that's neither here nor there. Hold on. What happened to me? Okay. So I want to take the integral, and all of a sudden my computer is going nuts here. Hold on. Why is this happening? I hope I don't have to reboot. I may have to. Let me close out as much as I can here. See if I can. Okay. So if I take the integral of that curved line, that function, and integrate it along the x-axis, it looks like I want to go from 20.5 to 31.
Right.
Okay. So, and that also needs to be opened and reclosed. Reopened and closed. In other words, when you take the integral of a function from one point to another, you get the area between the curve and the x-axis.
Right.
Okay? So, if I want this area, if I draw a vertical line right there, from there to there, then I'm going to integrate that function from 20.5 to 31. Now, do you have any questions as to how to integrate that? Let me move this up a little bit so I can In other words, that's fairly straightforward integral because you're just going to place of f of x, I'm going to write your function. Okay?
Right.
And we know that the integral of a polynomial, which is the sum of a bunch of terms, is the same as the sum of the integrals. Okay? Let me move this one over there so I can read it. In other words, if I want to integrate that, I'm going to integrate the minus 0.0759 x squared dx plus the integral of the second term of the polynomial, 4.48 x dx, same limits, plus the integral of the number. Is that minus 59.1?
Yes. Is this called integral by parts?
No, it really isn't. Integration by parts is kind of the reverse of the product rule. And I'm happy to work with you. I understand it. But this is not integration by parts.
Okay.
Integration is a lot more difficult than differentiation. With differentiation, you have a rule for every function that you can think of. It's either the product rule, the quotient rule, the chain rule, or the power rule. For integration, you don't have all of those things. You have a power rule if you have a simple polynomial, and we can apply the power rule to these easily. In other words, to integrate this, I add 1 to the exponent and divide by the new exponent. Okay, same thing with that. So let's integrate this. So the first term is going to be minus 0.0759 x cubed over 3. We're going to evaluate that from 20.5 to 31. And you know how to do these evaluations?
Yes. You plug in
top
the
number first.
Top number, then subtracted by the bottom number.
Yes. Okay. So the most difficult part of these is keeping track of all your parentheses and minus signs. Because since you're always subtracting, you have a minus sign there for sure. We got that minus sign there, so we're going to have lots of minus signs. But let's just set it up, okay? What's the integral of 4.48x?
4.48 divided by 2.
4.48
x squared.
Yeah, I always add the 1 to the exponent first and then just divide by that. I find that's the easiest way. You never mess it up if you do it that way.
Right.
And finally, the third term is a negative because I'm going to take that negative sign out front, which I could have done on the first term also. But just to illustrate that you can take constants out. So what's the integral of 59.1?
59.1x.
Okay. And evaluated at the same two limits. So we have that number plus that number minus that number. That's going to be the area under that curve.
Okay.
And we could go through all the arithmetic, but it takes quite a while, and I don't know if you want to spend your time doing that. Bless you.
Thank you.
I mean, you don't have any problem figuring these out, right?
No, I won't have any problem.
At this point, yeah.
And can we also quickly go over optimization?
Sure.
Since we recently had a test, and I had technical difficulties with that one.
Optimization, conceptually, is figure out your function that is to be optimized. Usually it will be a function of two variables.
Right.
There will be another function that you will be able to write that relates those two variables. Okay? I mean, a very simple optimization problem is how do you build a corral next to a river or a house where it only needs 3 sides? How do you optimize that? Well,
right. Can we do that?
Yeah. Uh-oh. Hold on. Oh, man. Just a second. Every now and then I have some difficulties with GoToMeeting. And the only fix I have on it is to reboot. I may or may not have to do that here. My mouse doesn't seem to want to control anything here. There it goes. You close out your page. Maybe by closing out a bunch of stuff. I'm going to close out my calendar. We'll see if that helps. Okay, we'll do the typical river problem. Okay. We're going to optimize. Now, if our goal is to determine the dimensions of this fence that gives the maximum area, then what is the main function we're optimizing? What's the area? What's the area of that corral?
X times y.
Okay, there's our function we're going to optimize. So, they always give you another piece of information, though, and that other piece of information is typically, okay, you have 1,000 feet of material, of fencing.
Okay.
Okay. Well, if you have you have to have one other piece of information. If you have 1,000 feet of fencing, then I know that 2y plus x equals 1,000. That allows me to make y a function of x or make x a function of y. And either one you can do. Just to be consistent, we'll work with x. I will solve this for y. So y is going to be 1,000 minus x divided by 2. So now I can plug that into my area function. So my area function is x times 1,000 minus x over 2. And now we have an area function that is a function of only one variable, x.
Right.
So all I have to do is differentiate that function, set it equal to 0, solve for x. And the reason is that my area function, in this case, you can tell it's going to be a quadratic, a parabola. Okay?
Right.
Well, by differentiating this function and setting it equal to 0, when we differentiate it, we're now looking at the slopes at any point along this parabola. The reason we set it equal to 0 is because that's where the maximum occurs, is when the slope of the tangent line is flat. It's equal to 0.
Right.
So by differentiating this, what is this? This is a equals 500x minus x squared over 2. What's a prime of x? In other words, first we differentiate the area function. What do you get when you differentiate that?
500 minus x.
Well, minus, yep, x. Okay. Now we set that equal to 0 because we're looking for where this derivative is flat. Remember, the first derivative is the slope of the tangent line. So we're looking for where that tangent line is flat, which will give us the maximum on that parabola. Well, in this case, x equals 500. Well, if x equals 500, we have 1,000 feet of material. These have to be 250 each. In other words, once we've solved for x, we can go back into this formula up here to solve for y. Or
Oh, right. Okay. I see where I was going wrong with that.
Okay, and there's our dimensions. That is the greatest amount of area you can make a rectangular fence using 1,000 foot of fencing material. In other words, where the perimeter is 1,000 feet. And that's actually a fairly common problem if you're a rancher. Is you have a certain amount of fencing material, how do you design your corral for your horses so that you give them the most amount of area?
Right.
Well, if it has to be rectangular, you do it like this. If it can be any shape, it turns out that spherical or probably hemispherical might work if you have a river on one side. But if you were designing out in the middle of the field, the answer is always a circle. In other words, a circle will maximize the area no matter how much fencing material you have, if you have to completely surround it.
Right.
And that's why pi is such a fantastic number in the universe, is because the circle is the most efficient shape. Circles and spheres. It's why all planets form as spheres and stars as spheres and everything. It's because that's the most efficient way to form a planet or build a corral in the shape of a circle.
Right.
Or whatever. Now, this is probably as simple as it gets for optimization problems. But the key to remember is that you have your main formula, and then you have your secondary formula. And I like to think of it in terms of that. You're always optimizing the main formula, and you're always using the secondary formula to make the main formula a function of one variable instead of two.
Right.
And these can get varying degrees of difficulty in terms of having a difficult optimization problem.
Yes.
Trying to think of another typical one would be this one. This is a pretty good one here, actually. This is y equals 3 minus x squared. Standard parabola moved up by 3 units, pointing down. Okay? And the question is what is the maximum size rectangle I can put under that parabola? Okay. Notice that if I draw my rectangle, is that a bigger area or a smaller area? Or I can draw it like this. Is that a bigger area or a smaller area? So it's not intuitively obvious at all how we draw that rectangle.
Right.
Okay. Well, what's our master function that we're trying to optimize? The area under the rectangle, right?
Right.
What's the function for the area under the rectangle? What's this point right here? Yeah, that's x. That's y. So the area of the rectangle is 2x times y, because the base of this rectangle is 2x. It's not x.
Right.
Okay. Well, we have y defined as a function of x up there. No matter where I'm at on this curve, y is always equal to 3 minus x squared. So now I can say the area of the rectangle is 2x times 3 minus x squared. Now I have my area function as a function of one variable only, and it's relatively easy to solve. A of x equals 6x minus 2x cubed. Let's differentiate that. What's a prime of x?
6 minus 6x squared.
Okay, now I'm going to set that equal to 0 because I'm looking for flat tangent lines. This is a cubic function here, so this function might look like that. Well, we're going to find two places where there's flat tangent lines. We're going to find this spot and we're going to find this spot. So it's going to be important for us to know whether we're dealing with this point. In other words, when you take the derivative and set it equal to 0, you're not always finding a maximum. You're sometimes finding minimums also. In other words, if you're starting with a parabola that looks like that and you find the flat tangent line, you're finding a minimum. If you start with a cubic that looks like this, you're going to find a maximum and a minimum. Okay, well, let's solve it first of all. So we get x squared equals 1. X equals
plus or minus.
Plus or minus
Plus or minus
1. Okay, so at x equal 1 is the answer. In other words, the minus 1 doesn't make sense. We're dealing with dimensions here. Even though you might think that the minus 1 would be over here, that's not really what's going on here. We came up with two solutions, and it's the x equal plus 1 that gives us the maximum area under that curve.
Right.
So it would be at 1, and what is y when x is 1? Y is 2. So that point is 2, that point's 1. That's the biggest rectangle you can fit under that curve. The smallest rectangle would be an x of 0. Notice that if x is 0, I don't really have a rectangle. I have a straight line. Even though y is 3, the area of that straight line is 0 because x is 0.
Right.
All right. That's the essence of optimization problems. You may get some that are harder than this. This is, let me just say one last thing about this. Okay? This itself is very straightforward. However, if I make it just a little more complicated, it really becomes tough to understand. Let me just do that before I let you go, because this is not that easy to see.
Okay.
Now what is the biggest rectangle that I can fit under that curve?
Can there be more than one solution?
I suppose there could be with this particular problem, but that's not what I'm trying to show here. I want to point this out because this is not that easy to figure out.
Yeah, since it's not off on the
what is the base
y-axis.
What is the base of this rectangle? If we know the intersection point is at 2, well, this point here
well, you could do it as
is x, right?
like, what's the function?
This
Okay.
point here is x, correct?
Right.
Okay. By symmetry, now let me, instead of saying that's x, let me call this dimension right here x. Okay? By symmetry, this one is also x. So what's the base of that rectangle's dimensions?
Z minus 2x.
This is a 2. Yeah. In other words, we know it comes back and crosses the x-axis at 2.
Oh.
Okay? So
Yeah, 2 minus 2x.
2 minus 2x, and the height of the rectangle is y. In other words, that's always y. But the base is a little tricky.
Right.
But it's the same problem. In other words, you're going to have the that function defined. So here's your area function right here. This is your primary function. And the only difficult with it is defining the base of that rectangle as 2 minus 2x. That's a little tricky to notice. But notice that even if I drew that rectangle like this, well, that's still x right there. That's still x, so it's still 2 minus 2x. So no matter how I draw that rectangle, the base of it is 2 minus 2x, and the height of it is y. Well, you're going to have some formula for this parabola, maybe y equals 2 minus, or 2x minus 2x squared, something like that. So you substitute whatever this function is in for y, and then you follow the exact same process.
Okay.
Differentiate it, set it to 0, solve for x. I doubt that you're going to get very many that there's 2 solutions. I haven't seen too many optimization problems where you can have 2 different solutions. There's always exactly one spot where this rectangle is the maximum. I suppose it's possible that, like the 2 dotted rectangles I've drawn there, I suppose it's certainly possible they could both have the same area and they are also the maximum. So you might come up with 2 answers. I don't know.
It's just unlikely.
Well, I shouldn't even say that. Let the math direct you. In other words, once I substitute this in for y, differentiate it, set it equal to 0, I may come up with 2 values for x because I'm going to have a quadratic. In other words, I'm going to have a cubic initially, but then after I differentiate a cubic, it's down to a quadratic, but we know quadratics have 2 solutions. If they're both positive, then you would have 2 solutions. But if one of the x's is a negative solution, then you throw it out. Because, again, we're dealing with dimensions here. X has to be positive.
Right.
All right. I'm going to let you go.
All right. Thank you.
You're welcome. I'll talk to you next Thursday.
All right. Can do.